In the last video, we used trig to determine how far away from shore that we were when we were on a boat. Let's try something a little different without just looking it up somewhere. How can we estimate the height of the Empire State Building? So first we should assume that we're standing on flat ground, that we could see the building, and that the building is standing upright. So the word upright contains the word right because it implies that you make a right angle with the ground. And let's say that, so maybe we're standing over here, and we have a phone GPS that we can use maybe to see how far it says we are from the Empire State Building, and let's say it says that we're 1 mile away. So this distance, this ground distance, is 1 mile. But I don't want to know how tall the Empire State Building is in miles. I'd rather know that in feet probably, right? So I'm going to write this distance here. Instead of 1 mile, I'm going to write it as 5,280 feet because that's exactly what 1 mile is. And I want this distance, which is the height, h, of the Empire State Building. And now you can begin to see that there's a right triangle in this picture here that wasn't there before, right? So if I just connect this last 2 points, you can see the hypotenuse. And we need a little bit more information. So maybe another thing we can do is point to the top of the Empire State Building and get somebody to take a picture of us and see what estimate the angle of elevation of our arm from the ground level. And maybe we do that. It'd be a crude approximation, but it'd be something. And maybe you get 11 degrees. And now we can use trig, right? Because relative to 11 degrees, we have the opposite side and the adjacent side. So the tan of 11 degrees is equal to h over 5280. And now we can easily solve for h. We just had to multiply both sides by 5280. So h is equal to 5280 times tan of 11 degrees. And you should just plug that entire expression into your calculator instead of, you shouldn't just plug in tan of 11 degrees and then just round that and then use that, because you want to round at the very, very end to make sure that your answer is as accurate as possible. So if you just plug that into your calculator, you'll notice the answer is about 1,026.3-ish feet. And if you look it up on Google, it is around that. And yes, we're done with the question, but if you notice, we actually have enough information to figure out everything else about this right triangle. We can figure out that angle, right? It's 79 degrees because everything adds up to 180 degrees. And also we can figure out this last side, this last hypotenuse, either with the Pythagorean theorem or more trig. But the point is we can fully solve this triangle. That's what it means to solve a triangle, to figure out all the sides and all the angles. And a lot of the time when we're doing trigonometry, that is exactly what our goal is. What we are given to accomplish that goal is going to depend on the problem. So the goal may always be to solve the triangle, find every angle on every side. But the setup is always going to look a little bit different, but they can be put into 2 general categories. This is the most common category, where you're given one of the non-right angles, right? So what you're given is one non-right angle and one side. It doesn't matter that it's the hypotenuse. You could do it no matter which side you get. In this picture, it's the hypotenuse, but if you get any side at all, and you get any angle that's not the right angle at all, you can solve the right triangle. So let's try to do it. So the last angle is probably the easiest part because all the angles have to add to 180 degrees. So 70 plus 90 plus what equals 180? It must be 20 degrees. And we need to find this side and this side, right? So maybe I'll give it name, this side I'll give it a name of x, and this side I'll give it a name of y. And now we can sort of exploit the fact that we know that that's 8 and that angle is 70 degrees in order to find x and y, but we have to do them one at a time. So let's find x first. So how can we relate x and 8 and 70 degrees? Well, x is opposite of 70 degrees and 8 is the hypotenuse. So opposite and hypotenuse, that should make you think sine. So sine of 70 degrees is equal to x over 8. And a lot of the time, that's the hardest part of this type of problem. It's just finding which trig ratio is going to give you the right relationship between what you know, 8, and what you're trying to find, x. Okay, so now that you have this set up, it's easy to get x. It's just solving an equation. So it's x is equal to 8 times sine of 70 degrees, which is about 7.52-ish, I believe. And now all we need to do is find y. Well, how can we find y? We actually have options at this point, because we know that x squared plus y squared is equal to 8 squared by the Pythagorean theorem. And we just found x, so we can use that to solve for y. Or we could do what we just did to find x to find y. We can use trigonometry. So how can we relate y to 8? Well, y is the adjacent side to 70 degrees, and 8 is the hypotenuse. So the cosine of 70 degrees is equal to y over 8. So we can use either of these equations to solve for y. And when you do, I believe you get y is about 2.74 or something like that. So that's the main setup that you're going to get. But sometimes you might get something like this, and this is a little bit more advanced, where you're actually not given any of the angles. So you don't know that's 70 degrees, and you definitely don't know that that's 20 degrees. You do need to be given something, though, right? So what you are given is just two sides of the right triangle. So let me just give you two sides. It doesn't matter which two sides. Let me say that this side is 5 and this side is 3. So what you're given here is just two sides. The last side is actually not that hard. So if I call that last side x, what relationship do we know between 3x and 5? The Pythagorean theorem, right? So x squared plus 3 squared must equal 5 squared. And you might also remember from geometry, one special right triangle is the 3, 4, 5 right triangle. And so if you remember that, or you solve this out, you will see that x must equal 4. And so we know that x is equal to 4, but then what are the angles, right? Like, what is theta, for example? It's hard to tell. But we do know the tan of theta, for example, right? Like, we know that the tan of theta is opposite over adjacent, or 3 over 4. And so we have some clues as to what theta could be, because we know that tan of theta starts off really small as theta starts off small, and then it gets really, really big as theta increases. And we also know that tan of 45 degrees is 1, and so 3/4 is less than 1. So we could at least maybe deduce that theta is less than 45 degrees. But how can we do better than that? How can we do a little bit better? Well, the way we could solve this exactly is with something called inverse trig functions, which we'll talk about in a later video. It's a bit advanced. But for our purposes, we built a table last time in the last lesson, right? There are tables out there that exist for much more values of theta, and they'll tell you what the sine, cosine, and tangent is, like this one. And if you use a table like that, you can sort of narrow down much better what the theta value is, and you could find that the theta value is, I believe, between 36 degrees and 37 degrees. So something in that range. And of course, once you have that, you could easily figure out like the range of like what this last angle has to be. And I know that's not exactly precise, but to be really precise, we need the advanced thing that I alluded to earlier, which we'll get to at some point. Now, let's go back to the Empire State Building question. If you really wanted to, you can physically measure the Empire State Building, right? Like, you can go to the top of the Empire State Building, theoretically, and just have like a really long measuring tape and like release it until it touches the ground and just see how tall the Empire State Building is. In theory, you can do something like that. How about we try to address something with trig that it would be impossible to do it? Let's try something a little bit more interesting. Let's try to estimate the distance between the Earth and the sun. That's a very long distance, and we definitely can't use a tape measure, even in theory, to measure that distance. So how would we do it? Well, first we should draw a world-class diagram of the sun, moon, and Earth. And obviously the moon and the Earth are drawn a little too big in this picture, but I'm doing that on purpose because I have to make some things clear later on, so just ignore that detail. But with that being said, let's say all we know is the distance between the Earth and the moon. It's 240,000 miles. And at this point you might be like, wait, how would I even find that out in the first place? Because this whole thing is supposed to be cool because you can actually kind of do this stuff. So how could you figure out this distance? Well, luckily for you, one of your homework problems after you watch this video is exactly using trigonometry to measure that specific distance. So you could use trig to get that. And let's say that we've already done that and we have that and it's 240,000 miles, okay? So using that, let's try to find the distance between the Earth and the sun. Can you think of how to do it? Well, maybe we should draw a triangle, right? That's probably a good idea considering we're doing trigonometry here. So if we think about maybe the distance that we're interested in, which is from the Earth to the Sun, we can call that distance d. And then we can, mark in the line that we know is 240,000 miles long. And then we're going to have enough information to sort of at least define a triangle. And so we have this triangle. Of course, this triangle is going to look different depending on where the moon is as it's like revolving around the Earth. But it's going to look like this at some point. And unfortunately, we don't know that any of the angles is right in this triangle. At least the Empire State Building is standing upright. So that was like, we use that to our advantage. Here, we don't know like where the right angle is. But what's interesting is it's actually easy to tell from Earth when this particular angle is a right angle. Why is that the case? How can we tell by looking at the moon when that's a right angle? Well, when the sun is shining on the moon in such a way that this is creating a right angle here, then it's lighting up the left side of the moon, and the right side of the moon here is totally dark. And so when you look at the moon from Earth, you don't see the right half of the moon. You just see the left half lit up, and you would see a half moon. And you can measure on Earth exactly how much of the moon disk in the sky is lit up. If it's exactly halfway, you know that that angle is exactly a right angle. So you could, if you want to do this in practice, you would have to wait for the next half moon, which you could do easily, right? They come around once a month. And so when it's a half moon, you should, from Earth, you could point to the moon, or use some, you don't have to use your arms, I'm just doing this to make a point. Obviously, you'd use some like high-tech instruments, but you could point to the moon, and you could point to the sun, and measure literally the angle between those two pointers. And if you measure that, it's not that hard to do that, you'll notice it's around 89.85 degrees, which is very almost right itself, and it kind of looks like almost right itself, right? And now we could use trig, right? Because if that's 89.85 degrees, then this is the adjacent side, and this is the hypotenuse of this right triangle. So that means the cosine of 89.85 degrees is equal to, what is it? It's, let's get this right. It's, 240,000 over d. And we have to solve this for d. And when we do that, we get d is equal to 240,000 over cosine of 89.85 degrees. And I believe if you put that into your calculator, you'll get that it's about 92 million miles. And the actual distance between the Earth and the sun is about 93.7 million miles or something like that. So that is a really darn good estimate. So that's pretty cool. Let's try something a little harder. Let's imagine that we are flying inside of this plane. Hopefully we're never flying inside of a plane that looks exactly like that one looks, but for better or for worse, let's say we are in that plane and we are flying above a flat road, and on one side of the plane on the flat road is car 1, and on the other side of the plane on the road is car 2. Is it possible from the plane to figure out how far apart are the two cars on the ground? Well, obviously we need some amount of information. And luckily for us, on a plane, there's a lot of instruments that tell you a lot of different pieces of information. One of those instruments tells you from the flight path, which we could assume that's this dashed line, and let's assume that it's parallel to the ground. There is an instrument that tells you how far you need to deviate from this flight path to get to any location outside of the plane. So it'll tell you the angle of elevation for points above the flight path and the angle of depression for points below the flight path. And since the cars are below the plane, these are both going to be angles of depression. And so based on this instrument, let's say the angle of depression to car 2 is 65 degrees, and the angle of depression from the flight path on the opposite side to car 1 is 75 degrees. And furthermore, obviously, there's another instrument on the plane that tells you how high off the ground you are, the altitude of the plane, and let's say that's given as 10,000 feet. Is that enough information? Can you figure out how far apart the two cars are? Well, it turns out you can. And the first step is to actually draw in the altitude, because that's going to reveal something key. So if this is 10,000 feet, not only is that 10,000 feet, we now see that this picture is essentially two right triangles. And we are the master of right triangles. And so what are we interested in? Well, we want to know the distance between the two cars, so the distance from car 1 to car 2. Well, if we think about these as two separate right triangles, and we think of this leg of this right triangle as x, and this leg of this right triangle as y, then the answer to our question, the distance that we're looking for, the distance between the two cars, can be expressed as x plus y. So now we just need to find what x is and what y is. Well, for that, we need an angle. Do we know any angles inside either of these right triangles? Well, since the flight path is assumed to be parallel to the ground, if this angle over here is right, then it must be the case that that angle is right. And if the angle of depression to car 1 is 75 degrees, then the leftover part of the right angle must be 15 degrees. And by similar logic, the leftover part of this angle, which lives in the right triangle, is 25 degrees. And now we could start thinking about trig ratios, right? So from 15 degrees, we have the opposite side, x, which is what we want, and we have the adjacent side, which is what we have, 10,000 feet. So that's tan, opposite and adjacent. And same for the 25-degree angle, we can relate the opposite side, y, which is what we want, to the side we have, the adjacent side, 10,000. And so we can write down tan of 15 degrees. That's going to equal x over 10,000. And similarly, tan of 25 degrees is going to equal y over 10,000. And so we can solve for x and y, right? So x is going to equal 10,000 times the tan of 15 degrees, and y is going to equal 10,000 times the tan of 25 degrees, which means x plus y is going to equal 10,000 times the quantity, if I factor it out, tan of 15 degrees plus tan of 25 degrees. And if you plug that into a calculator, I believe you get something around 7,343-ish feet. So that's how far apart the two cars are. So again, the point of trigonometry isn't just to find how far apart two cars are. Obviously, that's like not of interest to everybody all the time. But the point is, in situations in the real world that have nothing to do with trigonometry on the surface, it turns out that trig has this uncanny power of modeling those situations and telling you a lot about them. And in fact, we've only begun to scratch the surface of that. There's a lot more crazy, interesting things to come in the future. But before we can get to any of that stuff, you need to do your homework. And I'll see you next class.